Here we have a limit as x tends to 1 of the floor or greatest integer function of x plus 2 divided by x plus 1. Whenever you've got a limit that has the greatest integer function or the floor function in it, you probably ought to consider using one-sided limits. Even though this limit doesn't mention one-sided limits, you probably need to try them. So we're going to look at the limit as x tends to 1 from the right and the limit as x tends to 1 from the left. So recall what these mean. This means that x is bigger than 1, and this means that we keep x smaller than 1. So if x is close to 1 but bigger, then the floor of x will be 1, and this will be 2, and then this will go to 1 plus 1. So this is going to be 1 plus 2 over 1 plus 1. This x doesn't have the floor. This is just plain x. So as x tends to 1, it tends to 1. And then this is the floor, so you're rounding down to 1. Right? X is a little bit bigger than 1, but you round down to the next lowest integer, which is 1. Now, if x is less than 1, the floor of 1 will be 0. Right? Because what we're interested in are values of x that are very close to 1, but slightly less. So those are going to round down to 0. When I say a value close to 1 but less than 1, I mean a value like 0.9999999. Well, you get the idea. A value very close to 1 but still smaller is going to have a floor of 0. Now, this x is not inside the floor function, it's just a plain x. So when x tends to 1, whether from the left or the right, x is going to tend to 1. So this is 2 over 2, which is 1, and our first limit is 3 over 1. And since these do not match, this limit does not exist. Now we have the limit as x tends to 1 of the absolute value of x minus 1 divided by the quantity x minus 1. When you have a limit that involves absolute values, this is another opportunity for you to use the one-sided limits. You really want to consider using one-sided limits in the case where you've got absolute values. So we'll look at the limit from the right and the limit from the left. Again, where x is greater than 1 and where x is less than 1. Well, let's look at this fraction. You've got the absolute value of x minus 1 over x minus 1. Very often, x minus 1 and its absolute value are equal. Very often this is equal to this. The numerator and the denominator are equal. If they are not equal, then the only difference is that they have opposite signs. This is going to be positive, and in that case this will be negative. So they're either both positive, or the numerator is positive and the denominator is negative. Which do we have in this case? Well, if x is bigger than 1, the numerator and denominator will both be positive and they'll be equal, and that quotient will be 1. Now, in the case where x is less than 1, x minus 1 is going to be negative. The numerator is still positive. The only difference between the numerator and the denominator is that this is the positive version of this negative number. When you divide, the result is negative 1. Since these do not match, this limit does not exist. Now let's take a look at the limit as x tends to 0 of sine of 11x over 13x. We know what to do in the case where this expression and this expression are equal. So what we need to do is rewrite this limit so that that expression and that expression are equal. So the first thing I'm going to do is pull this 1 over 13 out front. It is a constant, so we are allowed to do that. Now, I need to make this x 11x. So what I will do is I will just multiply it by 11. Right? I just multiplied the denominator by 11 so that this expression and this expression would match. However, I've changed the problem we're looking at by multiplying just the denominator by 11. I also need to multiply the numerator by 11 to keep everything equal to what we started with. But instead of multiplying by an 11 right here, I'm going to move it out to the front, where I can call it 11 over 1. So that's 11/13. And then we have the limit as x tends to 0 of the sine of 11x over 11x. Remember that if you have the sine of an expression and then that is divided by that same expression, so you have the same thing here as you do here, and that expression tends to 0, that limit is 1. So we have 11/13 times 1, which is 11/13. Here we have the limit as x tends to -6 from the right. You know what that means. It means we're talking about values of x that are slightly bigger than -6. So on the number line, if that's -6 and that's -5 and so on, we're talking about x's that are very close to -6 but just slightly bigger. Alright, so what's going to happen here? Well, we have seen absolute value problems before. You know that x plus 6 and the absolute value of x plus 6 are either equal, or the only difference is that they have opposite signs, which is the case here. Well, if x is slightly bigger than -6, when you add 6 to that, think about what that's going to do when you go out on the number line 6 more units. It's going to place you slightly to the right of 0. All right, so adding 1 would put you at a point just slightly to the right of -5. Adding another 1 would put you to a point slightly to the right of -4, and so on. And if you add 6, you'll end up slightly to the right of 0. So x plus 6 is going to be positive. The numerator is also positive. Those turn out to be equal, and so that limit is 1. (1k), we have the limit as x tends to 3 from the left. We're talking about values of x that are slightly less than 3. So on the number line, we're talking about values of x in that region. And so we've got the absolute value of, the greatest integer function or floor of x divided by x minus 1. So what are we going to get here? Well, x is approaching 3, so the denominator is going to approach 3 minus 1. Right? We don't have to worry about rounding here since it's just a plain x. It's not the floor or x of x. Now the numerator is going to be, well, let's see, we're talking about numbers that are slightly less than 3, but they're bigger than 2. When you take the floor, you're going to get 2. So that should be 2 over 2, which is 1. We have the limit of f of x as x tends to 3, where f of x is defined piecewise. it's 6x minus 3 if x is greater than 3, and it is x squared plus 2 if x is less than or equal to 3. So, for a piecewise defined function and a limit at that separation point between the two pieces, which is 3 is the boundary between the two regions. Since we're looking at the limit at that boundary, we definitely want to consider using one-sided limits. So when we look at the limit as x approaches 3 from the right, here we're looking at x is bigger than 3, here we're looking at x is less than 3. So in this case, we're going to have the limit as x tends to 3 from the right of 6x minus 3, and that's going to be 15, I think. And then down here we'll have the limit as x approaches 3 from the left of x squared plus 2, which is 11. Those two do not match, so this limit does not exist.